So homework number 6 is due on Tuesday. I'll have an office hour in this conference room. It has to be at this time because there's no other time available for a conference room. And let's think, what else? So then I won't have office hours Thursday, and the exam is Wednesday in class. I mostly have written the exam. I've got to kind of probably narrow it down to a few questions. I'm going to have the TA take it, Rosie take it on tonight so we can catch any bugs that are in it. And then I'm not going to be here on Wednesday. She's going to proctor it. So hopefully if there's any issues, we'll catch it tonight. Okay. So topics, basically, you know, it's going to be similar to how the last one was in terms of the relationship between the material and the exam. So basically all the lecture notes and homework sets. If you need an equation, you'll be given it. So, you know, we spent a lot of time on density of state stuff, so probably there'll be a lot of stuff from that. For 0D, 1D, 2D, 3D systems, semiconductors, valence bands, conduction bands, doping, Fermi level, Fermi energy band gaps, conductors versus insulators, and how that relates to those properties, the Fermi-Dirac relationship, quantum confinement as we go into 0D, 1D, 2D systems, block theory and linear combination of atomic orbitals, and how that affects the quantum confinement and conducting and semiconducting properties. Probably a little bit of band diagram, not a lot. We didn't spend a lot of time on this. And then our last section here on semiconducting polymers, carbon nomenclature, graphene nomenclature, carbon nanotubes, which we'll cover today, and graphene, which we'll also cover today. Yeah?
Is the nomenclature
like what we ended with last period?
So do we need to know the derivations for each of these states, like the rules?
Which rules?
Like the density states, like do we need to know the derivations for that as well as like the...
Yeah, that's good to know. Yeah. Other questions? Yeah.
Well, we have like an equation sheet with all like the states.
If you'll be given it, you'll need it. I mean, if you need it, you'll be given it. Yes, that's what I meant. Yeah, so that table that we kept going back to where it was like the density of states, effective density of states, 0D, 1D, 2D, you'll definitely have that table. Yeah. That exact same version. Okay. So now as I'm thinking forward into the last third. How much of this stuff do you guys know? This Miller indices? You've seen this. A whole quarter on this kind of stuff, Miller indices. Okay. And so. Okay, so I wonder if that's a new convention because last year she spent a lot of time on it. So maybe we'll drop that out then if that starts to become boring. So we said 106 was all. Who taught that? Xuping. Okay. So you probably got a pretty thorough treatment then.
You got a treatment.
Okay, well that's kind of fine with me because that's not my expertise. So I would much rather go into like surfaces. How much of this, so this is a chemistry. Like if I said, I want you to be able to link a protein via a primary amine onto a nanoparticle. Like would you know how to do that via an N-hydroxyl succinimide? No? Okay, because that's like very practical kind of, yeah, okay. Okay, so maybe we'll swap out some of this with, okay, good, I'm glad I asked. Okay. Okay, so what we're going to talk about today then, carbon. Who's seen the hype curve? Has anybody seen the hype curve? A couple of you. So more than anything, these damn carbon nanotubes have just been, they're a classic example of the hype curve. And so it's your duty as scientists and engineers to be aware of how your colleagues sometimes can take advantage of the hype curve. So with anything, whether it's nanotechnology or what's really hyped right now in science? What? Bitcoin? Yeah. The microbiome, how much do you see about the microbiome, right? Like it's going to cure everything. We're going to do fecal transplants and we're going to do, just profile your This campus is building a whole building dedicated to the microbiome. And, maybe it will. Before this it was monoclonal antibodies and then circulating tumor cells and exosomes are right now like right here. And so anytime there's something, a new discovery in the field like fullerenes or carbon nanotubes or some kind of trigger, and this leads people to get really excited and imagine what we can do, and before you know it, we're building space elevators right out of carbon nanotubes, and that's now probably been 20 years ago. And so then you have this crash, and then the public comes back and is like, well, we've been spending, $50 billion a year trying to have you people build us space elevators out of carbon nanotubes. Where is it? We're going to quit giving you our money. And so then there's slowly this slope of enlightenment. And so then this is probably where we are now, well, probably here, like on carbon nanotubes. And now we're finally starting to like build something like bicycles out of it, right? Like something that's kind of simple and practical, but definitely is not all the way up here in terms of outlandishness of the invention. So just be aware of this. Not only, if you start asking people for money to do engineering, you kind of have to promise them big things, but you have to balance it with realism. And so be aware too, when people come and pitch things to you, right, of where they are on this hype curve, okay? So carbon, it is pretty amazing that this is the only element that exists in all of these different systems, from 3D, diamond, graphite, amorphous, 2D systems is graphene. You roll that up, and then you have a 1D system of carbon nanotubes, and then even smaller than that, things like fullerenes, buckyballs. And pretty much the difference is all in our SP2, SP3 hybridization of these different orbitals is what affects all these dramatic properties. And so the difference between diamond is dramatic both in terms of their electrical properties, their hardness properties, and their stability, right? But they're not that different, as you know, right? And so this is just a table of these different bond orders. This is one of the few slide sets that I stole quite a few from Andrea, because she had a pretty intense slide deck. Do we know what this means? This C, right? Like this conjugated bond, right? Yeah, exactly. Something like that. And so we've seen this, how an 2s come with a 2p orbital to create a variety of sp hybrid systems. So whether it's just a pure sp where we're combining with only one p orbital or multiple p orbitals, sp2, sp3, we've seen all of this. And we've also seen the ability to write the hybridization in terms of the wave functions, right? So this is for an sp system. And we realized that the sp orbitals were a combination of the two s orbitals and then the positive and negative lobes of the respective z orbitals, okay? And then we saw this as well for an sp2 system, sp3 system, right? So this is all review. So what's kind of remarkable about graphene, and believe me, this is not me. I hate when there's that comma or apostrophe there, which just should not be there because it's not possessive, it's just plural. So in graphene, right, all of the carbons are sp2 hybridized, right? So there's an sp2 here, an sp2 here, and an sp2 orbital there. Right? So when I first saw these years ago, right, and you looked at just what graphene looked something like this, right, and I saw this kind of representation, I just assumed that it was like any other kind of hydrogen or organic nomenclature. And so I just assumed that when I saw this, that there implied that there were hydrogens here, which is not what happens, right? There are not, just because this is drawn like this in graphene, there are definitely not hydrogens there. Now, I mean, if you look at something like the basis of a lot of steroids, like testosterone, has a structure that looks like this, and then stuff go off it. There's definitely, if it's implied that if there's an unsaturated carbon, that there is a hydrogen there, but not in graphene like this. Okay. So sp2 orbitals find sigma bonds, and the bonding orbital associated with each sigma bond is occupied by 2 electrons, right? Yeah, because you're sharing the 2 electrons from either the adjacent s's and the p, x, or y orbitals. So what's left over is this remaining pz orbital that has 1 electron that can participate in pi bonding with neighboring electrons, right? So this is going to be coming out of the board and into the board, right? But what happens, and this is just trying to illustrate this through a different approach. So here, this red is indicating the sp2 electrons, and this kind of fuzziness is illustrating how these the pz orbitals so if this is another carbon and then another carbon, how these don't particularly form pi bonds, right? It's not like we're not forming pi bonds across graphene, but what these electrons do is become completely delocalized across the surface of graphene. And so this electron can, with almost no resistance, can hop from pz orbital to pz orbital to pz orbital. Yeah.
So would that act like an electron density cloud?
Yeah, I mean, very similar to very similar to gold, right? Where you just have electrons that are completely delocalized. Yeah.
So would it be slightly less conductive than like a metal with similar configuration?
You know, it's hard to compare them directly because it's hard to make a monolayer of gold like this, because when you have a monolayer of gold, you just have fewer electrons. And so, but when you do an absolute measurement of it, I don't know how it compares, but I think it's quite competitive. I think it's second only to silver.
Is the conjugated bond less conductive than its top?
Is the conjugated bond less conductive? No, because this is not really, I mean, you don't even really want to think about this as a conjugated system, not like, you know, this. These are even more delocalized than a semiconducting polymer, because this has 0 band gap, right? This, if we looked at the band gap, so those semiconducting polymers previously were still, I mean, polyacetylene was down to 2 millielectron volts, right? But here, we're like a metal, where there's no band gap. Yeah?
What does the x-axis mean? Why do we have triangles?
Ah, good question. So here, because what this is representing, and we just don't have the full time to get into it, but what it is showing is this is in our K space. Okay, so this is the momentum. You can think about this in terms of momentum for these different electrons with these different wave functions. Okay, and so whereas because of these are the symmetry of graphene, that's why it comes to a point like this. Yeah.
So it seems like the pi bonds, or not really pi bonds, but in pi bonds we have p and z orbitals that just kind of overlap and form this common wave function.
Yeah.
Probability in between. So in this case, we see that same exact thing but stretched out in 2 dimensions with localized nodes.
That's why, I mean, our density of states is a flat, right? For this 2D system, if we were going to plot our density of states, right? It's a 2D system. You have one set of density of states as a function of energy, right? If you think back to how we plotted it. Yeah.
So is each carbon like have a charge on it, or?
No, it's not like it's a carbanion.
So they only have 3 bonds that does not charge?
Yes.
So does like the valence electron satisfy it?
Because it's so spread out that there's no net charge. So yeah, valency is satisfied. Yeah. Yeah, in the back you were.
You said that the material has sp2 carbons, right?
sp2.
Does that imply that on the edges of the material you'll have sp carbons?
Good question. What do you have on the edge? You know, the way this stuff exists in nature is it stacks, right? And so that's graphite rather than graphene. And so I would think that those kind of satisfy themselves on the edge. I suspect in reality you have a whole host of different situations, some where you're hydrogenated, some where you have sp2 situations. I don't think that we can make any hard or fast rules about what happens on the edge. But that's a good point. Yeah.
So are you suggesting that these are not a series of double bonds to make them sp2?
Correct. They are not a series of double bonds. Yeah. To think about this as like something like this is inaccurate. Yeah. Because you don't have that many, there's not that many electrons, right?
So it's just, I guess going
It's
back
a completely delocalized set of electrons. The pz orbitals have completely combined into a single wave function. That's why we're showing this representation here where these are different k values, right? When you move your energy up or down, then you can add or subtract more solutions to the Schrodinger equation, right? That's why when we go up or down, we have this broadens out. Okay? Yeah.
Stuff result in Cooper pairs somehow.
In what?
Cooper pairs.
I still missed it.
Cooper pairs.
Cooper.
Pairs.
I don't know. Yeah, I've got to look into that. Yeah.
Is the bond length like that of a single bond then between graphene?
Bond length. So bond length is, let's look at this one. I like this one. So if we think about the units, this being the unit cell of one graphene. So here's graphene A, graphene B, and then another graphene A. So the bond length in carbon is about 1.4 angstroms, right? This carbon-carbon bond. And then the distance between two is about 3.3 angstroms. How does that compare to a regular carbon-carbon bond? Yeah. It's longer. So if we go back here, shorter than a single carbon bond, which makes sense.
So it's the length of conjugated carbon bond then?
Yeah. Okay. So think a little bit more about the unit cell. Good, you've had crystallography, thorough treatment of crystallography. So unit cells. So this is how this community has defined a unit cell, is this kind of parallelogram. And you could move it back and forth, right, to include any points, right? But this is the basic unit are 2 carbons in a unit cell, okay? And so then, and this is, I probably should have shown this before I did the nomenclature exercise, is to think about these 2 vectors, A1 and A2. So A1 and A2, and these are kind of arbitrary, but what they do is connect next nearest neighbors. So not the exact neighbors of one carbon, but the next nearest neighbors. Okay, so these two atoms per unit cell, lattice vectors A1 and A2, which can start from any starting carbon, right? Could start from here, could start from here, 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 right? The origin doesn't matter as long as you define where 0, 0 is, okay? And so that's why this is vector A1, this is vector A2 when we drew this in class, right? So that's why we're skipping every other carbon, because that's how the vector is defined, okay? Okay. So while we're on that, why don't we jump right to this thing that I wanted to do from the homework. So what if we wanted to calculate the diameter of a carbon nanotube? So if we hold this picture in your brain, right? We're dealing with these hexagons. And then if we think back to some basic geometry about a hexagon, so here's a hexagon, and within this hexagon, we can have this 30, 60, 90 triangle whose dimensions would be 2, 1, and the square root of 3, right? Or 1, 1/2 square root of 3 over 2, right? So therefore, we can start to define the vectors, the x and y vectors within A1 and A2 based on the carbon-carbon bond. Okay? Let me write it down and hopefully it'll make sense. Okay, so this is the x and y component within A1 and A2. Okay, and A2 we're calling negative by convention because it's going in a different direction. We could, of course, switch which one we're calling A1 and A2. Okay, but we see where these numbers came from based on this geography. This distance right here is the square root of 3 over 2. Or square root of 3 over 2 times the carbon-carbon bond length. Okay? So now, if we want to start to get an expression of the length of, or excuse me, the diameter of a carbon nanotube, we can think about the chirality vector, which is the sum okay? So if we had this long carbon tube, say we had something like this, right? We would just add up the number of n's times A1 and m's of A2, right? Where n and m are just this nomenclature, right? Okay. So then this would equal 2 pi r or 2d, right? To take the absolute value of this, because this is the absolute value of this squared, starts to get us closer to the three-dimensional arrangement of this tube. Yes?
Did you mean to say pi d instead of 2d?
Yes, thank you. Equals pi d. Yes, thank you. So therefore, diameter equals over pi. Okay? So you guys probably remember vector math more than I do because I had to study hard to learn this. So if we do this, if we tease this out, we get n squared a1 right? Okay, so now how do we use this relative to this expression? Yes?
Can I ask what's B for that?
B is your bond length. So what we're expressing here, so let's say, in this basic geometric expression, if we want to call it 1, call the hypotenuse 1, that's where we get these relationships. Right? And now, but here we're changing it relative to the bond length, the carbon-carbon bond length here. So this B carbon-carbon is the bond length. Does that make sense?
Does that mean the direction too?
Yeah. Yeah. So this is the x and y components of these vectors. Three over 2 is the yes, the bond length of
Is this pointing to the next nearest neighbor, so you have to go 1/2 and then the bottom in the x direction, right?
Yes, it's solving this for the x direction as opposed to the y direction. Okay. So then if we remember that when you multiply so then we're just going to start to multiply this together. So n squared okay, so this is all that. This 2mn this is this.
Aren't those b squared today?
Yes. And then this is the same thing as the beginning term, only we have m's instead of n's. So this is the same as 9/4 b squared plus 3/4 b squared. Okay. So then this is n squared 3b squared plus, we can write this as 2mn 3/2 b squared. Right? So this is This is 9 over 4 plus 3 over 4 is 12 over 4 is 3, right? And this is 9 over 4 minus 3 over 4, which is 6 over 4, which is 3 over 2. Yeah?
What exactly is vector A? Because we have a A1 and
What a vector is A1 and A2.
on your group on the right where you have A times vector A times vector B.
This was just me reminding you of how this vector addition works, or this vector multiplication works. There is no B here. This is just the generic rule. Yeah.
What's that like component 1?
Yeah, so we could think of so we could also write this as A1, A2, right, equals the, do you get what I'm saying? I just wrote B to keep it simpler. So what we're doing here is multiplying the x component of A1 times the x component of A1, the y component of A1, y component of A1. Here, it's the x component of A1, the x component of A2, times the y component of A1, the y component of Y3, or Y2. Yeah. So we could also then write this as square root of 3b squared plus mn square root of 3b squared plus m squared square root of 3b squared, right?
Go from 2mn 3 over 2 to mn 3.
That cancels.
Why did it become root 3?
Why didn't we say that again?
Why did it become root 3?
Because I moved my square out here.
Okay. I'm back on.
Yeah. So getting closer then. So remember that what we were deriving an expression for is the absolute value of this chirality vector. And so now we can put this over here after taking the square root of it. To derive an expression for the diameter of a carbon nanotube as being the square root of 3 times the bond length over pi times n squared plus mn plus m squared. And this is the expression for that first question in the homework. Okay? So that's kind of nifty, right? And hopefully it kind of makes sense that you're just essentially you're adding up these x and y components of these individual vectors based on the number of times you have these vectors. And then that gives you a diameter. Okay? What else? So we talked briefly about how there's different kinds of carbon nanotubes and how that this naming convention is based on what it looks like when we would fold these. So a 10-0 carbon nanotube where this carbon essentially replaces this carbon to loop it on itself would have a different structure than if we had gone from 0, 0 to 5, 5, right? And so this MN nomenclature, NM, constitutes a unique name for the tube, right? And if it's N0, then the carbon-carbon bonds are parallel to the axis of the tube, okay? And this results in a zigzag pattern on the edge, right? This is the zigzag that you're looking at, right? Whereas in chemistry, they call this armchair. You could kind of think of like you're sitting in this, right? And like this is one arm and this is the other arm, right? Doesn't look very comfortable. So these are the kind of, there's these two extremes from N0 to where M and N are equal, okay? In between, these are non-chiral carbon nanotubes, okay? Anything in between are chiral carbon nanotubes, okay? And that just means that they have left and right-handed variations, right? Where not every carbon that is bound to your central carbon is the same. These are achiral because every carbon that is bound to every carbon looks identical, okay? Yes?
For armature, isn't the red parallel to the tube axis? So, like, is it zigzag? Like, is the tube axis like the y direction, or?
Zigzag parallel to the tube axis. That is kind of vague, isn't it? Because you could, is this the axis or is this the axis? Because both of them have carbon-carbon bonds that are. Yeah, let me. Think about it more in terms of how it looks on the end, in terms of zigzag or armchair, and B, whether the symmetry of this plane of carbons runs right through the center of the tube. Then it's definitely this armchair design. So here's how it would look if it's chiral. See how this no longer completely runs down the exact center of the tube? Whereas in this armchair design, you could follow this kind of honeycomb structure right down through the center. Okay? And then in a zigzag configuration, it depends how you draw your red parts here, right? But you could go back and forth, back and forth, back and forth, or this way, right? Yeah.
Does the armchair morphology have a greater tensile strength than the others?
I don't know about tensile strength. I just don't. Yeah. Would it make sense that it would? I would think that the chiral would be the least strong out of all of them. But yeah.
Like the zigzag is only a zigzag, like, so the zigzag is zigzagging in perpendicular direction in the armchair in that direction, and the armchair is the opposite.
Yeah, I mean, the way it's drawn here, it's opposite. But look at it down here, it's the same thing. If you look at the end, where this is zigzag and this is this armchair design. And then chiral, you can discriminate because from armchair, because this is not, this has a chiral angle, right? How do you calculate the chiral angle, you ask? Well, oh, I have it in here somewhere. It's in the book. Maybe I didn't get it in there. Ah, yes. Okay, so we're not going to derive this, but you can then calculate a chiral angle for using M and N, and you can express it both as a sine or a cosine, but there will be a chiral angle. Okay. What else did I want to hit on? Conductivity. Okay. So tubes are metallic, so meaning zero band gap, if the M minus N or N minus M is a multiple of 3. Okay? Now I wish I had a more satisfying explanation for why, but next year I will, but right now it's that so it makes sense that different chiralities have different different configurations, right, and different degrees of overlapping of the pz orbitals. And it just turns out, without spending a whole period on the block function to show this analytically, that as the orientation and alignment of the pz orbitals change, you can decrease or increase the band gap. And when these conditions are satisfied, m minus n or n minus m is a multiple of 3, you have a metallic-like carbon nanotube. Okay? So a zigzag of 6, 0, 9, 0, 12, 0 would all be conducting, meaning they would be metallic. Also would 6, 3, 9, 6, 12, 9. Okay? But something like 13, 9 would be a semiconductor. Yeah.
Would it still be zigzag if it was 0, 6, 0, 9, 0, 12?
The way I understand it, yes. Yeah. Yep. Yeah.
What are the highest end patents?
How big can you make these? Yeah, I don't know, but there has to be an upper limit to these. Probably the people who study it make them, and they're very short-lived, I would think, because at some point it just becomes more energetically favored for it to fall out, or to be a 2D system, right? Yeah. Yeah. Let me see what I can find. So then there's this expression for chiral carbon nanotubes. What is the band gap? So what the band gap for these conducting, there would not be a band gap, right? So here we're looking at density of states for a metallic conducting tube, and see how it never drops to 0 energy, right? But for a semiconductor, we have a band gap between the conducting band and the valence band, okay? And we see this kind of 1 over square root of E type of relationship that we saw for the density of states in 1D systems before, right?
Can you prove this using the block equation? Or a version of it?
This would be the approach, is to look at those linear combination of orbitals. Yep. Yeah.
So how controllable is it? What kind of tube do you make? Like how controllable are other values of
Not very. And that's why this has not reached the peak of expectations. Partly it's that experimentally, when you actually go to make these, how well does the tube maintain consistency across the whole length, right? What keeps it from getting smaller, bigger? How do you keep impurities out of it? And the other issue is they're much more energetically favorable to be multi-walled rather than single-walled. Meaning like this, where you have a tube inside of a tube inside of a tube, right? As opposed to a single-walled carbon nanotube where there's just one layer of carbon. And so because this is more energetically favorable, it just has more carbons, more electrons around it. That hampers the ability to get really long, pristine carbon nanotubes. We used to buy these from like the guy who won the Nobel Prize, his company down in Texas, and they were messy. And we tried a lot of different companies, and they were messy. And so this is still, this is why, of all the topics I wanted to, I always like to introduce the hype curve, but I felt like it's appropriate here. So the shorter you make these, the more controllable you can have. Now, that doesn't mean that they're still unusable, right? So maybe you go from this like astronomically high tensile strength to something that's still really damn strong, right?
So how do you like apply and measure like the tensile strength of a carbon nanotube? Like is it tensile? Is that strong tensile strength like in terms of the single nanotube like?
Yeah, a lot of that is theoretical. You can do the conductivity measurements using this kind of field effect transistor where you just create an electrode. And so the electronic properties are actually much more easy to measure than the true, to physically test the tensile strength, right, is pretty hard. You could use, people have used piezoelectric materials, stuff like that. Okay.
I have a question.
Yeah.
How far off is the experimental versus theoretical?
For which?
And tensile strain, shape?
I mean, that's a really open-ended question, and it depends a lot on what you're studying, which parameter. You can't. It's hard to draw any generalizations. Yeah. So some other things to just bear in mind, you can do doping just like you can with any other kind of semiconductor. People have put in boron and boron and nitrogen into these carbon nanotubes to control the band gap. And then how do you modify these? For especially using them in anything that's aqueous, these things are incredibly hydrophobic. So one approach is to start to go in and break carbon-carbon bonds using strong acid and heat, and then you can start to put some kind of reactive group. But generally, by far, the more common approach is to take something that's equally hydrophobic that is then linked to a hydrophilic end and put it in water and sonicate it. You know what a sonicator is? Yeah, it's like the electric toothbrush where it sits there and vibrates, and you just vibrate the hell out of it. And over time, these hydrophobic groups will adhere to the surface, and then you can then have this hydrophilic group, and then do chemistry on that. Yeah.
So on the previous page, you were showing just multi-wall carbon nanotubes. Can you do similar chemical modifications on single walls?
On multi-walls?
Oh, on single walls, because it's the same multi-wall.
Yeah, it sure looks like it's drawn like, yeah, that doesn't make much difference. Your interior is going to remain hydrophobic, and no big deal, because after this point, you've coated it in a hydrophilic layer. Yeah.
We have a multi-wall carbon nanotube. Can the tubes slide really?
Not really, no. They're pretty rigid, because you have a lot, you can start to think of those wave functions then as also starting to overlap to a degree. Yeah, right? Yeah.
So how does a multi-wall, having a multi-wall nanotube affect the conductive properties of it? Does that affect it at all?
Yes, and it will definitely, so let's think about that. If you're adding more electrons, you're broadening the density of states. Yeah.
And for when you're doping it and tuning the band gap, what are the actual applications of that?
Well, I mean, imagine if you had this kind of field effect transistor, and by increasing or decreasing the band gap, then you start to have this circuit, or this, think about it like a transistor, that's what it is, right? And then you can control the transistor's behavior by doping this individual nanotube, right? Okay, so maybe we'll do more on carbon in the next third if we've got everything else covered. But this will be, so exam will be through here. And any last questions? Okay, so I will see you in a week, because I won't be here Wednesday.